Okay, so last time we did this as an example. We had a cube 8 centimeters on this side, and then we had the density of wood 0.4 gram per cubic centimeter, and then we said what portion of the wood gets wet. Then we argued that because it's cubical, the ratio of the volumes is equal to the ratio of the height that gets wet to the total height of the object. We call that HO. And then since the density is 0.4 over 1, so 40% of the cube gets wet. And then the ratios of the volumes is equal to the ratios of the height. And then H prime is 0.4 times 8, and then that's 3.2 centimeters. So next we want to see if the object, instead of being a cube, its density of the wood is still 0.4, and it's in the shape of a sphere. The sphere density is 0.4 gram per cubic centimeter. So the diameter is going to be, we'll make the diameter 8 centimeters. So the radius is 4 centimeters. So from the top here to the bottom, diameter is 8 centimeters. But since it's in the shape of a sphere, now we want to know the portion that gets wet, and it's not necessarily going to be 3.2 centimeters, right? So we want to find an equation for the volume of a portion of a sphere. So we'll draw the sphere like this. And so we want to know the volume of a portion of a sphere like this as compared to the volume of the total sphere. So the best one to do this one is in the Cartesian coordinates, x, y, z. So slice off the sphere like this into a small slice. And say, what's the volume of that? And then we can integrate that, let's say from here, you can call from here to here h. And then the total radius is r. Right? And then integrate that from h to r. And then come up with an equation for what the volume of that portion of a sphere is. So then the volume of this thing is going to be dV. It's going to be the volume of the area of the surface area. Right? So if this is y and z, right? Because it's a circle like this. So the distance from here to here, the general distance from here to here is going to be x, right? And then from here to here, it's going to be, this one is going to be the radius of that disk as we're integrating along all those disks. And that's going to be square root of y squared plus z squared, right? And then this is going to be the distance like this. It's kind of coming out of the board. So the radius, the volume is going to be pi r squared dx times the thickness of that piece, right? And then the r squared is going to be y squared plus z squared, and then you don't have to worry about the square root. And then we can use the equation of a sphere, that x squared plus y squared plus z squared is equal to the radius of the sphere squared. Then we can say y squared plus z squared is r squared minus x squared. Then we can substitute that there. Now if we want to check to see if our procedure is correct, we can integrate this from 0 to r. So if I integrate all these slices from 0 to r and I double it, right, then that should give me the equation for the volume of a sphere, which is 4/3 pi r cubed. So then you have here 2 pi, integral of r squared, that's going to be r squared x, then integral of x squared, x cubed over 3, 0 to r. So if that comes out 4/3 pi r cubed, then that means our procedure is right, and then we'll do the actual what we want to do. So volume of a sphere is equal to 2 pi. Then you plug in the r cubed minus r cubed over 3. Then when you plug in 0 for x, you get 0. Okay, then you're gonna get your volume of sphere is 2 pi, 2/3 r cubed. So 4/3 pi r cubed. Okay? Nice smiley face. Okay, so now we want to find the volume from a certain distance, we can call that h, let's say, all the way to r. So now we shouldn't double it anymore. We're only finding this volume. Then we can go from h to r. See, that'll give us the volume of a portion of a sphere, right? Then I'll have here v, we can call that v prime, this guy, v prime, right? And then that's going to equal pi, the integral of that r squared x minus x cubed over 3, h to r, and then pi. Then I can put the r again, minus, and then I can put the h, r squared h, plus what? So when I subtract, of course, I'm going to get this is minus, but then when I subtract, this is going to turn to plus, right? Because it's under the parentheses. So plus h cubed over 3. And then, so this tells me v prime is equal to pi 2/3 r cubed minus r squared h plus h cubed over 3. So that tells me, depending on what the h is, right, I have a general equation. Of course, if I put h as 0, what's going to happen? This is going to disappear. Then you're going to have 2/3 r cubed pi. Then if I double it, that gives me the volume of the sphere again, right? So now, going back to here, so now let's apply Archimedes' principle. V prime over v is no longer going to be h prime over h. So this is only true for if it's a rectangular cubical object, right? Now I'm going to set that equal to the density of the object over density of water. So 0.4 over 1, which is 0.4, right? So I'm going to say v prime divided by v, which is what? The total volume of the sphere, 4/3 pi r cubed, that's equal to 0.4, right? And that's, now we want to find what h has to equal, right? So the pi and the pi cancel. The 3 goes up to the top. So then you have your 2/3 r cubed minus r squared h plus h cubed over 3. I guess I could cross multiply the r cubed, 0.4 r cubed. Right? So I reciprocated this. I took the r cubed over to the other side. I could factor this in, see what we get. 3 cancels the 3, so 2 over 4, that's going to be 1/2 r cubed minus 3/4 r squared h plus 3 cancels the 3, 1/4 h cubed is 0.4 r cubed. Right, and then what happens? 0.5 half minus 0.4, right? This is 0.5 minus 0.4. That's going to be what? 0.1, right? Zero. So of course, depending on what the r is, you have a certain solution for the h. I guess I could multiply everything by 4, so we don't have a fourth. I'll have 0.4 r cubed minus 3 r squared h plus h cubed is 0. Now we can put the radius of our sphere, right? So I tried to mimic the sphere so that the overall diameter of the sphere, we can kind of superimpose the sphere like this, you know, so that the height from the top to the bottom is 8. So now I want to see if the sphere sinks in deeper or does it float up higher. You see? And then compare it to the answer we got there, which was 3.2 centimeters. Okay. So then if the radius of the sphere is 8, I mean the diameter is 8, then the radius is 4. So I could put R is 4 centimeters here. Well, 4, I'm going to put 4 here and then square it. So 64, 4 cubed is 64, right? Minus 16 times 3 is 48. Then what's that going to be? 16, 1, 24, 25. Okay, now put that into your TI solver, solve for H. Question?
I have a question.
Yes.
When you integrated the sphere, at the beginning, you did pi r squared minus x squared dx. Then when you got the B sphere, you did 2 pi r cubed minus r cubed over 3. My question is, why did you integrate or get an r cubed when you had r squared?
How did I get an r cubed? When you put the x, the r here, you get r cubed.
No, but the first one, before that, it's r squared, yeah, minus x squared. And the dx, I get that. And you integrate it, you get
R squared x.
oh, this is cool. Yeah.
Yeah, because r squared dx, the integral of that is r squared x.
For sure.
It's like r squared is a constant. Yeah, good question. Okay, so now put that in solver and we have it give us an answer. Let's see here. Maybe there might be a couple answers. 3. Oh yeah. Okay, there's a negative answer, which we don't want. Then another one says I got a positive answer. It's curious that you get one positive answer that is a decimal place. So that would be what, 0.53 centimeters. So it's like basically almost 0, huh? 0.53 centimeters. So remember, from here to here is 4 centimeters. Doesn't seem like that. So here, oh, this can't be the answer either.
Yeah.
Because it can't be larger than 4. So then the negative answer can't be the answer. That one, wow, that's weird. Very small. Okay? So now what is the picture looking like? If from here to here is 0.53, how much of it is sinking under the water? So let's draw a final accurate picture. So at 0.53, that means almost like 3.5 centimeters is sinking under the water. So it's looking like this. So almost the center is like right here. So like the center of the sphere is like right here, you see? And then from here to here is 0.53. Hold on, right? Is that right? Oh, no, hold on. The center is here.
It's right over the water.
So it's like this. Hard to draw a sphere. So this is the center, but how much gets wet? So the portion that gets wet is 4 centimeters minus this. And then compared to the cube, 3.2 centimeters gets wet. So which one sinks in deeper? The sphere. Does that make sense now? First, it's trying to understand what the answer means and draw a visual representation of the answer, and then asking yourself, should that happen? Should the sphere sink in deeper?
Makes sense.
Why? Why does it make sense?
Well, the way I would think about it is it seems as though there's more weight like right over it, where a square would have like more surface area, so there would be like more water pushing it up.
Yeah, and because the sphere, if the ratio of the volume has to be some number, but the bottom portion of the sphere doesn't have a lot of volume, it doesn't displace a lot of water, so it has to sink in deeper in order to displace the same amount of water that a cube has to have displaced, right? So it goes in a bit more. It's not that much more. That was 3.2, and this one was 3.46. So if you subtract 0.266, so the sphere sinks in 0.266 centimeters more. Right? Now you can do any kind of shapes, you know. So next time you see a bowl in the water, in a swimming pool, you're not going to think about it any different. You're going to start to do the integration in your head. Right? In the summer, right, you swim, you have those balls you play with, right? So depending of course on the shape, then different shapes will sink in different amounts, right? So this is a good problem that illustrates a little bit of integration again, and then illustrates the meaning of the Archimedes Principle as applied to floating objects. So now we can do sinking objects. Sinking objects will be objects whose density is greater than density of water or whatever fluid that you're placing them in. So then what's going to happen to them? They're going to immerse themselves, right, fully in the fluid, and then they're going to start sinking. So how much water or fluid will they displace? A volume equal to their own volume. You see? So the buoyant force, and this is their weight. The buoyant force is equal to what? Remember, Archimedes' principle said that the buoyant force is equal to the weight of the fluid that they displace. So it's the density of the fluid. Let's just use water for now, but if the fluid is not water, you replace it with the density of that fluid. So density of water times gravity times the volume of the water they displace, which is equal to their own volume. So volume of the object, you see? It's equal to the volume of the water. Okay, but what is their weight equal to? Then their weight is equal to the density of the object times gravity times the volume of the object, right? So which one of these two is greater? Their weight or their buoyant force? course, their weight. You see. So then we have here, that means they're going to start sinking. So we have here mg minus fb is equal to ma. If we want to calculate the acceleration, how fast they sink, right? How do we calculate that? This is going to be dOGVO, FB is dWGVO, and then what's their mass? Their mass is, density of the object is their mass over their volume, right? In this chapter, a lot of things, we're still applying Newton's laws, but we're expressing everything in terms of density and volume instead of mass, right? So then their mass is going to be dO times VO. Right? So that means the acceleration that they sink with, that the rate at which they sink, the volume of the object cancels, and then we can say A is equal to dO minus dW over dOg. So the denser the object, right, the faster they sink, right? So let's see if this equation makes sense. If dO is approximately equal to d water, if your density is about the same as the density of water, what happens? The acceleration is 0, or close to 0, let's say. Right? But as the density of the object gets much, much bigger than the density of water, what's going to happen? It's almost as if you could ignore this guy, right? So if this is much bigger than that, then the acceleration approaches what number? The acceleration is less or approximately equal to what? Well, if this cancels, dO cancels, and then acceleration approaches g. Right? So it can never be greater than g. So if you're very dense, you're going to sink in water at a rate almost approximately equal to gravity, right? And then if your density is similar to water, then you're going to not accelerate. So this is kind of our case. Humans, our density is much denser than the fluid we're in, which is air, in a sense, right? So if you take me and you drop me from the top of a building, at what rate will I accelerate down? An acceleration equal to approximately g, right? Because air is not going to be able to supply enough buoyant force. But now if you drop me in water, my density is not that much denser than water. So I will accelerate in water at something less than g, of course. See? Okay. Then there's a term called the apparent weight of the object. What is the apparent weight of an object in water? That one is kind of like this portion of it. This portion is the apparent weight, because it's your actual weight minus the buoyant force on you. So we just say the apparent weight apparent, is equal to dOGVO minus dWGVO. Now we can get an equation for that. We can factor out the VO, factor out the G, and then VO, replace it by M over dO. Right? So instead of like canceling here, to calculate the acceleration, we cancel the VO. Here, instead of canceling it, I'm replacing it by M over dO. Weight apparent. So VO is going to be mg over dO. And then mg is your actual weight, right? weight apparent, weight actual, dO minus W over dO. Okay, so all of these come from, the derivations come from the simple fact that the buoyant force is equal to the weight of the displaced water. But the weight of the displaced water is equal to density of water, gravity times volume of the object, because the object will displace its own volume, right? and then after that, the derivation is pretty simple. Okay, how about something like this? Let's say you have I'll make it the same size as the other one. Hollow spherical ball of radius 4 centimeters made of aluminum. Let's see, something like this. So I'm giving you the hollow spherical ball, the radius of the ball, whose density, I'm giving you the density of aluminum. What is the acceleration of this ball when you place it in water as it sinks to the bottom? Now, is it possible that I can fill it with some gas that is light, and then I could manipulate the density of that gas such that it accelerates down at 1.1 meter per second squared? And then how about differently? Can I do it so that the gas is even less dense and the ball and the gas together rise up and accelerate at 1 meter per second squared? Are those scenarios possible? Yeah. So you can imagine that that could happen depending on these equations, right?